We'll get started. I mean,
I
that
haven't
way we.
started studying for this quiz. Okay, wait, where am I going?
Hey,
You guys,
MG.
yeah.
Shruti said her phone died,
Oh,
so
no worries. That's fine. Um, and I'll record this, so if she needs to come back and look at it later, that way she can do that as
okay.
well. So do you guys just want to look at the the problems? Uh,
I think we should do a few problems from each like section so we
okay,
know we get them.
sure.
And also we should go over like because some sections have like harder questions in the end of the section, so we
Hmm.
should make sure to do those.
And then I'll open up the problems as well. So you can take a look at that. Let me have my annotate thing here so I can easily work with this. Oh my gosh, there's a lot of people. Okay, I wasn't expecting this many people to show up. That's fine.
They're all confused. That's why. Every one of us is confused.
I feel so bad. Um,
I mean, it's not your fault.
no, I know. It's like it's stuff that it's hard. It's hard stuff to wrap your mind around, but it's okay. We'll get through it. Um,
I love that the slide says, could we make our life easier? Like, yes, we could by not having this quiz.
So I'll just go over these things real quick. You know, derivative of a constant, 0, because simply think about it this way. The rules, you can always just think, instead of memorizing rules, just think, okay, if I have a function, right, and then if I just plot a constant c, the slope at every point is 0, right? That's why the derivative of a constant is 0. Now, what if I have c times f of x? So if I have d over dx of c f of x, I can just pull that constant out because essentially it's a multiplier, right? The constant you can think of as a multiplier, and that rate of that multiplier isn't changing over time, which is why I can just pull that constant out. So if I had 5x squared and I'm trying to take its derivative, I don't need to, like, I can just think of the 5 separately and just take the derivative of x squared, which would just be 2x. Roshi Dash has entered. That's an interesting name.
Roshi?
So this is 2x, and then I can go back and multiply the 5x, so it becomes 10x, right? So it's an easy way to just think of it as a constant, as a multiplier. Same thing when we add and subtract functions, it's one function added to the other, so I can think of the function in terms of its components, and then I can take the derivative of each of the components and then add them together. So we can definitely do all of that. Okay. Derivative of product. Okay, so this is the product rule. The product rule is very simple, right? If I have d over dx of f of x times g of x, it's very simple. It's just f prime of x times gx plus g prime of x fx. Okay? The way to think of it is if I have one function times another, I'm going to take the derivative of the first one, keep the second one, then add the derivative of the second one, keep the first one. So if I have x squared times x cubed, this is what I'm going to do. I'm going to do 2x times x to the third, which would be x to the fourth, plus 3x squared. This would become 3x squared times x squared, which is 3x to the fourth. Okay? So this would be, what? 5x to the fourth. Now, I chose a simple example. In reality, you shouldn't be using the product rule for this, if I'm going to be completely honest. What you should be doing is turning this into just x to the fifth, and then taking its derivative, which is 5x to the fourth. So whenever you can avoid using these complicated rules as possible, try and avoid it. Try and simplify it first. And whenever you can do something like this, where you can directly turn it into something simpler, do that first. Then resort to the product rule and stuff if you need to. But I just use this to show you that it can be done that way, and that's the way you should be thinking about it. Now, quotient rule, the way I like to think about it is if I have, it's a funny mnemonic, but it works. If I have f of x over gx, I just think this, okay, so I need this here. Okay, so I just think it's low d high minus high d low over low low. I'm going to write that down. low D high. Just say that 10 times and it'll get stuck in your mind forever. Mr. Clarity taught me.
Wasn't that last year? Wasn't that from last year?
Yeah. Didn't
Yeah.
Mr. Fusco tell us that?
Okay, yeah, he must have brought it up as well. Mr. Clarity taught it to me, and it was in 8th grade, and it just stuck ever since. Low D high minus high D low over low low. So what this is low, so gx times f prime x. Gx, so low D high minus high f of x, D low, g prime x, over low low. Low low is just low times low, so that's g of x squared, right? So that's your product rule. And honestly, once again, every single time you use the quotient rule, I said product rule, I'm sorry, it's the quotient rule. Every single time you use the quotient rule, don't write out. If you need to the first couple of times, go ahead and write it out, but generally you don't need to think about it like this. So once again, if I see something like x to the 5th over x cubed, once again, the easier thing to do would just be to simplify it and then use the power rule. But for the sake of this, I'm going to think low D high times 5x to the 4th minus high D low 3x squared over low low. Low low would be x to the 6th, I believe. Now, numerator, this would become 5x to the 7th. This would become 3x to the 7th, right? So if we do 5x to the 7 minus 3x to the 7, we get 2x to the 7 over x to the 6. I can cancel x to the 6 and subtract 6 from the power, so I get 2x, which makes sense because x5 over x3 is x to the 2nd power, and its derivative is 2x. Okay, that's how I like to think about it. And guys, feel free to stop me if you ever have questions. Just interrupt me if you need to. It's easier to do that than to wait until the very end. So just interrupt me if you need to. All right, are we good with all of this stuff so far? Okay, all right, I'm gonna move on.
I think I know you're like going through, but I don't know if this is like for anybody else, but I think the most confusing thing for me is the what's it called? The differentiation thing. Yeah, basic differentiation. No, not that. Yeah.
Like the rules, or
hold on.
Like, are you talking about recognizing the limits as derivatives?
I think the whole like open
like this
interval, closed interval thing.
Got it. Okay.
I think that was what was really confusing for me. I think
okay.
It's in the PowerPoint, but I just thought I would point that out.
I see what you're saying. So the way it goes back to that idea of continuity, right? So the things that we need for a function to be differentiable are it needs to be smooth and continuous. If it has a cusp, this is a cusp. The reason why we can't differentiate this is because A, the slope approaches an undefined, because a straight line is not differentiable. So the slope and the left-hand slope and the right-hand slope are different. Same thing with an absolute value function. If we have a point, I don't know if we would call this a cusp. I don't think we would call it an absolute value function. I don't think we would call that a cusp. But the main thing here is that the slope approaching from this side, as you can see, isn't the same as the slope approaching from this side. So when we go back to that idea of open and closed intervals, that has to do with the continuity part of the definition, right? So say, for example, we have a function defined here, and it looks like this, okay? This is a closed, and obviously this is, so this right here is closed, right? Because it's defined here. And then it's technically, this goes to positive infinity, so it's an open, but don't worry about that too much. We're more worried about this point, right? Because this is where it gets confusing. The thing is, this is closed. AP would say that this is continuous. IB would say probably not, because the left-hand limit, there is no left-hand limit in this case, right? You guys see that? How there's only a right-hand limit here, there is no left-hand limit. But what AP says is when we are defining the interval as a closed interval and we're cutting it off right there, potentially there could be another part of the function that keeps going, but we don't know. So we're going to assume that the other part of the function is there, and we're going to assume that we're going to forget about the left-handed part of it. So AP says that, and AP says that we can consider this continuous, and even IB and AP, both of them say we can calculate the derivative at this point. Okay? They say we can calculate it because it's closed. Now, if this were an open interval, if this were if this was a hole and it went like this would not, you can't calculate the derivative here because it's not defined, and therefore it's not continuous. Okay? So that's the difference. Similarly, if I had this going on and the function went like this I can't differentiate, but this I can. At this point, I can differentiate this now because it's a closed interval now. Does that answer your question, Alina, about the closed and open intervals?
Yeah, I just when would we use it? When would we say whether it's opened or closed? Why does it matter?
So why does that matter? Because sometimes you'll have a function in real world scenarios. Sometimes you have a function that might not be defined for up to x equals 1. Let's say the only time it has to do with time, maybe. So we'll say after 1 hour, water starts pouring off of whatever, right? Then we start the function here, and then we draw whatever it is, right? We continue drawing the function. Now, if the question asks us, what is the derivative, or what is the rate of change of this function at x equals 1, if it was not defined, if it was an open interval, we would have to say we can't calculate the derivative. But if it was closed, we can calculate the derivative. That's the important point. It's just to know that if it's open, we can't calculate it, and if it is closed, then we can.
Okay.
So we covered that stuff. Good. Quotient product, we did that. Okay. Power rule is very simple. I'll just do a quick rundown. You know, if I have 3x to the 10th power, that would be 30. I should be writing d over dx, but for the sake of time, I'm not going to write it. I'll just put an arrow here, and I'll assume that you can see that. So 3x to the 10th is 30x to the 9th. It's derivative. Okay? I think that's pretty obvious. This is just showing it using the limit definition of a derivative, how you can show that. But once again, you don't need to be able to prove it every single time. Just have the intuition for it, why it does work the way it does. Okay, power rule is also true for negative numbers. So in that case, if we have something like 1/5 x to the -2, what would that be? That would be -2 over 5 times x to the -3. And I can write that as -2 over 5x cubed. Okay? Usually AP doesn't need you to simplify it down. IB, I'm not really sure of the requirements, so we'd have to ask Ms. Raja what the proper way is. I think she likes things simplified, and I think the way she prefers it, it looks nice. But for the sake of AP, once again, let's do another example. If I have something like x to the half, like the square root of x. Remember, you can also use the power rule with irrational functions. So if I have square root of x, I can write that as x to the half. That's derivative would be 1/2 x to the -half. AP would say that's fine. You can stop right there, and that's enough. But I think for the sake of IB, and I'm not sure about this, so ask Ms. Raja, but the proper way to write this would be 1/2 root x. And then if you want to be really, really proper about it, then you would have to rationalize the denominator, and you would have to multiply both numerator and denominator by root x, which would get you to root x over 2x. Okay? So that's I guess, the proper math way to write it. But AP doesn't care. AP is fine as long as you stop there. Okay? Does the power rule make sense to everyone? And how you can use negative numbers, irrational numbers, everything. Okay. Good. I'm going to clear this right now and move on. Trig functions. These you just got to memorize, all right? My Siri is in French, so whenever I say anything that resembles the version of Hey Siri in French, it starts ringing. I'm sorry about that. So you just have to memorize these. The derivative of sine of x is cos of x. You can actually see that, right? Like this is the worst picture of sine of x, but just deal with it for now. think about it like the rate of change of this, literally it matches it, right? Because the slope here is 1, right? The slope here is 0. The slope here is -1. The slope here is 0 again, and so on and so forth. You see how it, like, literally it looks like cos of x if you think about it conceptually. So the derivative of sine of x is cos of x, but then the derivative of cos of x is sine of x, because here we started a derivative of 0, so that could either be positive or negative sine of x, we don't know yet. Here we're 0, so I'm going to plot a 0 there. Here we're -1, right? So do you see how normally sine goes here, it goes up from x equals 0, and instead the rate of change of cos of x goes down. So whenever you're thinking of derivatives, always think in terms of slope fields. Like, conceptually, that's the best way to think about them, just slope fields. So that's how you can think about these, but really the easiest thing to do is just memorize these. And then, of course, the derivative of tan of x, if I'm not mistaken, is sec squared of x. Correct me if I'm wrong. But once again, if you forget this, you know, the easiest way to do it is just take the derivative d over dx of sine x over cos x, right? And then we can use the quotient rule. So why don't we actually do that? I think that's a good practice, just to practice with the quotient rule. Well, what we're going to do is we take low d high, so cos x. D high would just be cos x, so this would be cos squared of x. So low d high minus high d low. The derivative of cos x is negative sine x. So minus sine x times sine x is minus sine squared of x. So if I have a minus sine squared of x here, the minus and minus become plus. And I know I'm doing a lot of these calculations in my head. The only reason I'm doing it is because if you're going to take the AP exam or IB exam, you should get used to doing a lot of these calculations in your head, because you just don't have the time to write out every little minus. So, you know, just make it a habit to start thinking of this in your head. And then in the bottom, we have low, which is cos squared of x, right? Now, does anyone remember, using the identities we learned, what that Mr. Fusco taught us last year, what the numerator would be, what it would simplify down to?
That equals 1.
Exactly, 1. And that's our Pythagorean identity. And in the bottom, we have cos squared of x. And if we have the reciprocal of 1 over cos squared of x, we look for the letter that doesn't start with a c, and that would be secant. So this would be sec squared of x. And that's why the derivative of tan x is sec squared of x. This is the only reason we worked it out right now, is because we just wanted to practice the quotient rule. But ideally, you should have this memorized. And then the other ones, the reciprocal ones, like what is the derivative of cot x, sec x. Usually we don't need to know those, but you know, then again, you just have the cheat sheet that's in the PDF, so you can always refer to that later. Okay, any questions so far? All right, I'm gonna move on. Exactly what she did right here. And then these are the derivatives of cot, cosec, and sec. So you can memorize these, I guess. I mean, once again, the other thing is, you don't need to, I think the thing is, you don't need to make a conscious effort unless you're just really bad at memorizing things. You don't need to make a conscious effort to memorize it. I think the easier thing to do is just apply them, and the more you apply them, they just become ingrained in you. You don't need to make a conscious effort. Alina, were you going to say something?
No, never mind.
Okay, all right. So we talked about this, right? You take, if you take the derivative of f plus g, that's f prime plus g prime. Same thing if you take the product rule, and then the quotient rule. We talked about those. And here's the cheat sheet. Let's go over each of these real quick.
Is this the sheet you were talking about?
Yes, this is a sheet I'm talking about. It's also, I think it's also on the PDF version of the PowerPoint. So
she said to print this, right?
Yes, write it down, print it. It might be easier to write it down because, you know, writing helps you memorize, so you might want to do that. So this right here, this is the power rule, we know that. Now the derivative of the absolute value is interesting. Why? Because the absolute value of x, it looks like this, right? really the derivative of the absolute value of x is just -1 for x is less than 0, and the slope for x is greater than 1 is just 1, right? That's why it's absolute value of x over x. If we take this, it'll always equal -1 if x is less than 0, or +1 if x is greater than 1, okay? And the other important thing to remember is since x is in our denominator, x cannot equal 0. And that makes sense, right? Because when we take the derivative, there's a sharp, the function is not smooth at x equals 0. Oh, here's another thing. When we say a function is differentiable, we have to be specific about it. We say the function is differentiable for all x in R except for x equals 0 here. Because it would be a mistake to say that the function overall is not differentiable, because we can actually take the derivative here, or here, or here, or here, and so on and so forth. So that's where the intervals that Alina was talking about comes in. Because the interval is here to here versus here to here. Now, the only reason that 0 doesn't work is because even though it has a left and right hand derivative assigned, they're not equal to each other. Whereas if the function was only, here, let me just draw it here. If the function was only this, and it was a closed hole here, even though we don't draw the other half of the equation, we can say here that the function is differentiable at x equals 0 because it's a closed interval from here to infinity, and we're assuming that it's differentiable here.
So if it's just differentiable if it has a derivative?
Yeah. Sorry. I thought that was, differentiable literally means has a derivative.
Okay.
Yeah, that's so that comes from the word so this branch of calculus, there's two branches of calculus. One is, so this is actually a pretty funny concept. If you break down calculus literally all it is slope and area. That's all calculus is. It's slope and area. Slope is the one big branch called differential calculus, differential calc, and differential. We use the word differentials for all of these dx's. So whenever you see d over dx, dx is what we call a differentiable. A differential is an infinitely small change in x or an infinitely small change in y. It's a differential. So Leibniz basically said, instead of saying delta y over delta x for slope, why don't we say dy over dx to represent infinitely small changes? So that's what the differentials are. The other branch of calculus is called integral calculus. And integral calculus deals with an area. So when we later learn about it, what you'll learn is integral calculus is saying that's where we use the sign called the summa, and say, for example, what is the area under the curve from 0 to 5 of the absolute value of x, and basically you'll just find the area under the curve. And I won't go into depth into this now, obviously, but the interesting thing is that there is something called the fundamental theorem of calculus, which relates this and this, which shows that slope and area are somehow connected. And that's very fascinating, but I won't go into it anymore right now because I don't want to confuse. But that's just a cool preview. Now, exponential functions, the derivative of e to the x is just e to the x. And that's one of the fascinating things about it, is just its rate of change is itself. Now, when we take a to the x becomes a little interesting because it's still an exponential function, but then this ln a pops in. Why? And I'll show you that right now. Do you guys remember the chain rule? So if I have f of g of x, the derivative of this is f prime of g of x times g prime of x. So what this is saying is I'm going to take the derivative of the outside function, put the inside function and keep it intact, and then multiply it by the derivative of the inside function. So if I have a to the x, I'm trying to find its derivative. I need to work its way into a form of e to the x that I can work with. So what I'm going to do is I'm going to write this as, how can I write this? I can write this as e to the natural log of a, right? I can write this as e to the natural log of a to the x power. Does that look right? Yes, because natural log and e are inverses, so this cancels it out. So essentially, this is just a to the x. Do you guys see that? I think you guys see that. I'll just assume that's a yes.
Yeah, sorry,
okay.
yeah.
That's fine. And then what we're gonna do is we can write this as, so if we're gonna use the chain rule, right? There's a very easy way to prove this. I forgot how to do it. I think what you would do is just, you would say,
It's okay, MG. We don't really need to know this.
Okay, yeah, well, don't worry about this right now. If I remember, I'll come back to it later. But the main thing.
Sorry.
Go ahead. Go ahead.
I don't mean to interrupt you.
No, you're fine.
I think, like, I don't know. I'm just like, I'm not trying to assume about everybody else, but I think we get it. I think I just like need to do like problems.
Okay, sure. Yeah, we can do that. Do you guys want to do that?
Yeah.
Yeah, we'll do that then. That's definitely. Yeah, no, I understand, definitely.
I don't want to speak for everybody if someone has a different.
No, yeah, you're right.
Okay.
That sounds good.
I think questions 13 and on are the problem area.
All right, we'll get there. So the only thing to remember here is just, refer to this table. Obviously you have your trig stuff here. Don't worry too much about this stuff. This stuff is not really needed. And then ln of x, this is another one you should know just off the top of your head. The derivative of ln of x is just 1 over x. So just keep that in mind. All right, we'll go to the practice problem so that, I don't want to waste your time or anything. So, okay, which one do we want to take a look at? Did you guys try any of these?
I think Ashwin just said 13.
13? This one? This number 13?
I've been doing like kind of 13 and on because we did like up to 12 in class.
Okay.
Yeah.
So for these, you shouldn't be using the product or quotient rule. If you're using the quotient rule, you're doing too much work. What you should be doing here is you need to factor this out. So here, what I'm going to do, I'll open up Paint. That way I have a little bit more space to work. And also, I'll say this again later, but we have 10 minutes left, and I have the free plan. So once this meeting ends, just use the same exact link to rejoin. All right? All right, so what I'm going to do is I'll take a screen clipping of this, if I can. Let's try this.
These, I just wanted to, what we were doing in class was that we just, like, separated it, like, for each one.
Yeah.
Like, for 12, it's, like, 15x to the power 7 over 3x plus 21x to the
Okay, yeah, that works too.
Okay, that's what, like, our breakout room was doing in class. It was, like, Karan and Anish, I think. But
got it. Okay.
Make sure that was, like, acceptable.
Okay, so I'll show you a way that I think is pretty good. So you can definitely break it up, and essentially that we're doing the same thing here. But what I'm going to do now is y prime. What I'm going to do is I'm going to factor, well, instead of y prime first, let's just deal with y first. I'm going to factor out x to the -4. And that's going to serve the exact same function. So if I factor out x to the -4, in the numerator I'll have -22 x to the -1 minus 17 x to the -7, right? You guys see how I got that? And then in the denominator, we'll have 21 x to the -4. And now what I can do is I can cancel out the x to the -4. And now I'm left with -22 over 21 x to the -1 and minus 17 over 21 x to the -7. Okay, do you guys see that? Now when I take y prime, I can just use the power rule, and this will become 22 over 21 x to the -2 plus 17 over 3 x to the -8. You see how I got that? Because the 7 comes down here, 7 The 7 and the 21 cancel, so we get a 3 in the denominator, and that's how I got the 3 down there. I just, once again, I'm trying to do these calculations in my head, and that's a good habit to build right now. Does that make sense, how we got this? Okay, good.
Did you write x to the power of -4?
Where would be the x to the power -4?
Like right at the beginning, like y equals.
So why did I do x to the -4?
Yeah.
Because what I'm trying to do is I'm trying to get rid of the x to the -4 in the denominator so we don't have to use the quotient rule.
Oh,
That's why
okay,
I factored out an x to the -4 in the numerator so I could cancel it.
Okay.
Okay. And that's the exact same approach I use with the rest of these. Even the ones that have fractions, like let's try number, here. Let's
I've
try.
been doing these, and sorry.
Go ahead.
Yeah, one thing I've noticed, even if like the exponent becomes really ugly, like you try to cancel it out, it's still better to just reduce everything into the numerator.
Definitely.
Right?
Yeah. So let's try number 16 real quick. That might help clarify things a little bit more too. That didn't work. Whereas, I really like snipping tool until Windows like started this whole snip and sketch business. I don't know if you guys use snip and sketch, but the snip and sketch stuff is kind of getting on my nerves. Okay.
Wait, I have a
anyways.
question. I'm so sorry.
Go ahead.
Do we need to know how to the homework we did like last week that we turned in? Is that like part of it?
I don't think, because she didn't say it was due.
Part of no, like the homework that we turned in. The derivatives one?
Yeah, that one?
Yeah, do we need to like know like
Oh, yeah, you should probably be able to know that stuff for the quiz.
I think that like some of those on there were like really confusing for me.
Okay, all right. Yeah.
Maybe
so
it was just me.
We'll do that and just we'll look at some of that in just the end.
These seemed like a little bit easier to me.
Wait, which assignment were y'all talking about?
The definition of derivatives problems.
Yeah.
Oh, like the limit definition?
Mm-hmm. Yeah. We'll take a look at it right after this.
Like the ones where it's like the slope of the tangent line.
Sure.
Like
Sure. Yeah, that one was harder. I'll say that one was harder than this one. This one, because like, these are just following rules, and we can follow rules easily. That one is more conceptual in application. So what I'll do for that one is we'll just take questions that people had trouble with, rather than go through every single one, because once again I don't want to waste people's time. We'll do number 16 though real quick, just to show what I was talking about. So this one I can write as x to the half minus x to the 1/3 over x to the 1/5. Now, this requires some thought, right? So you can do what Alina was talking about, where you break it up into the fractions, where you can do x to the half over x to the 1/5 minus x to the 1/3 over x to the 1/5, and then simplify it from there. Or you can think about it as factoring x to the 1/5 off of the numerator, and then you can eventually cancel it. So that's what I'll do. You'll get the same exact answer. It's conceptually the same thing. But this is where you have to think. Because what power, so 1/5 plus what equals 1/2 is what we have to think here. So it's a little bit more mind stuff. So I'm going to think, okay, 1/5 and 1/2, the common denominator is 10. So 1/5 is 2/10. 2/10 plus what equals 5/10? Well, 2/10 plus 3/10 is 5/10. So I'm going to get 3/10 here. I'm going to pause right here. Does everyone understand how I got 3/10 here and how 3/10 plus 1/5 equals 1/2? I just did this in my head. Once again, if you're not comfortable, literally just plug it into your calculator.
Wait, can you do that again?
1/2 Sure. I'm not, once again, I'm going to talk about how I see it in my mind. I'd rather do that than write everything out on the board, because it's important that you start to visualize things in your mind. I'm trying to factor out x to the 1/5, right? So I have to think x to the 1/5 times what equals 1/2. So if I think x to the 1/5 times what equals x to the half, it's a matter of adding the exponents. So I have to think 1/5 plus what equals 1/2. In other words, what is 1/2 minus 1/5? If I take a common denominator of 10, that would be it would be 1/2 minus 1/5. So I would have 5/10 minus 2/10. 5/10 minus 2 over 10 is 3 over 10. And that's how I got the 3 over 10 here. Does that make sense?
So you factor the 3 out of 10 out of there?
I factor the x to the 1/5 out because I want to be able to cancel this x to the 1/5 with the x to the 1/5 here.
Oh, okay.
And once again, if this doesn't make sense, then you can do what's here. We're doing the exact same thing because right here, what you're doing is x to the 1/2 over x to the 1/5. You would be doing the same thing. You would write that as x to the 1/2 minus 1/5 minus x to the 1/3 minus 1/5. You'd have to take a common denominator for the exponents, and you'd write x to the 3/10 minus x to the, so that would be what? 3 times 5, 5 times 3, 5 minus 3, 2/15. And then you would have to, take the derivative of these individually. So this would become 3/10 x to the negative 7 over 10 minus 2 over 15 x to the negative 13 over 15. So that's how you do that. If you want to do it this way, same idea. I'm just actually this way might be more simpler because you can think through it a little faster and write it out. But same idea here. This will be x to the 3/10 minus x to the 2/15, because what I'm going to think of is I'm going to think 1/5 plus what equals 1/3. Well, 1/5 is 3/15. 3/15 plus what equals 5/15? That's just 2/15, which is why I put the 2 over 15. So then the x to the 1/5 and x to the 1/5 cancel. We get this, and then obviously if you take the derivative of this, that equals that. Does that make sense? The other option would have been to use the quotient rule, but boy, you don't want to use the quotient rule when you don't have to. Okay? All right. Hopefully this made sense, all of this. And once again, you just got to do it. Did you guys try any of these? Did any of these seem difficult that you want to go over before we jump back to the other one? Okay, we have less than 1 minute, so I'm just gonna go ahead and end this because I hate starting to explain one thing and then it cutting me off. So just rejoin using the same link. All right.